Hello everyone and welcome to this first video of the new series about Kotlin design patterns and best practices. What this series is about. In this series we are going to see how we can use different design patterns and best practices in real life projects. What we are going to build in this first part is a chess game. So this is the application that we are going to build. As you can see, we have the board and the pieces, and you have like a normal chess game with all the correct rules of a chess game. The chess game rules are a really good example to use different design patterns and best practices, and it's really good to improve your thinking. What we are going to use in this tutorial, so we will use object-oriented programming, we'll use inheritance, also we are going to use some functional programming as well as test-driven development, only for a single piece, not for everything, but yeah, you can repeat the same approach for the different chess pieces. Also we will use the factory design pattern as well as a copy of the builder design pattern. We're not going to use the original version of it, but we are going to use it to build a DSL. In Kotlin we can have DSLs, which is a better builder design pattern. So we are going to use KMP wizard to generate a new project. You can use the wizard or any other way, so it's just makes things easier. I'll choose the project name, project ID, and I put Android, iOS, desktop, and web, and just you can download the project and open it in IntelliJ. So after opening the project, you'll get something like this, and this is just an empty composed multi-platform project. So we are going to work mostly on desktop because it's faster and we don't need to open emulators and so on, so we can have a better development experience. So let's delete everything. So I'll just keep this up function and I'll delete everything here. Okay, so let's start by building our logic. So let's build the pieces logic. We will have a piece interface. So there is a lot of common things between pieces, so that's why we will think about having an interface for pieces. Things like colors, each piece has color, position, each piece has a position. We can move pieces. Also we will need to get the available moves for each piece, so when we click on the piece we will get the available moves. So all of these things are common between pieces. So the only different thing is the available moves is different. So each piece can give like a different available moves depending on its position and its type. So we will create an interface of piece and we will have all of these common things in place. So sometimes people ask about abstract classes and when we need to use interfaces and when we need to use abstract classes. Like you can change interfaces in most of the times with abstract classes, but you don't need to. Like abstract class is much powerful thing, and if you don't need to use an abstract class, just use an interface. So keep using interfaces until you have to use an abstract class. The biggest advantage of interfaces is that you can have multiple interfaces implemented in the same class, but that's not the case for abstract classes. You can only extend a single abstract class. So that's why we try to use interfaces more, and they're just much simpler and they works on 99% of the cases. So there is no need for abstract classes in this case. So let's start by creating a new package or folder or whatever. I'll call it pieces, and we will create the new piece interface. So here we have this interface. So the first thing is the color. We have a color for the piece, so we can have a color, and of course not composed color, but we are going to create our own enum class color. Okay, I think I need to disable this code completion because it will make things. Okay, sorry. So we will have an enum class color, and we have white and black. So why I put this enum class here inside the piece interface, because if we try to use the piece interface, you can just type piece.color.white or black, which is more readable and easier to like, it's easier than something like piece color or something. So so we know that this color is for this piece interface. Okay, so then we will need a drawable. So each piece has its own image. So let's add a drawable here, which is a drawable resource from composed resources. Of course, by getting the project from the KP wizard, I have the composed resources dependency. But if you can't import it, just check your build.gradle and make sure that you have compose.component.resources implemented in common main. Okay, so what else? We have the position. So each piece has its own position. So there is different ways for like people handling the case of chess game. So you can have the positions, like all the positions of the board, and then inside the position, like you can have a class for the position or for the spot or for the square or whatever, and inside this class you can have a parameter which is the piece. Does this position has a piece or not? And you can take another approach, which is having the pieces, the available pieces, and inside each piece you have the position, which is, I think, a better approach, because instead of creating an instance for every spot in the board, which are like 8 by 8, we just need to create instances for only the pieces, which are 32 pieces, which is much less than the number of spots. So I think it's like both ways works, but having pieces and having positions inside pieces is much easier. So that's the approach that we are going to take. We will have a position inside each piece. You can have an X and Y or offset or whatever. I'll use int offset because we need an X and Y with integers. We don't need the float offset. Okay, so that's it, I think, for the properties. We need the function of get available moves. So we will use this method for getting the available moves of this piece, which is going to return a list of int offset, which are the positions of the available moves. And also, for this to work, we need to, like, the piece needs to know the information of the board. So let's say that we are going to move this this pawn, or like this one can move, but maybe we are trying to move this one. So it needs to know that there is another pawn in front of it, so it can't move there, but there is another one in the diagonal, so it can capture it. So the piece needs to have the informations about all other pieces. So what we are going to pass here in the get available moves is all the pieces, like a list of pieces. So the piece can have this information and can return the correct available moves. Okay, I think that's it for the piece interface. This should be enough for now. And yeah, we can start building our pieces. So let's start by the pawn. So I'm going to create a new class. I'm calling it pawn, which implements the piece interface. And let's pass the color to the constructor of the pawn. We can also pass the position. So the color and position, like, we need them as parts of the constructor. We can either, like, we can pass it this way, or we can just do this. So val position and equal position. So both are correct, but yeah, we can make it simpler. So for the drawable, we will have a check. So if the color equal color white, we will have the white drawable, else we'll have the black one. But also we can make this check much easier. I always, like when working with enum classes, I prefer having this is white, which is get this equal color dot white. So this is really useful, like makes things easier. Also is black, and the same way maybe I can add the type explicitly here. So this can make our comparison much easier. Like we can have color that is white and else is black. So for the drawables, I'll put the link of Figma assets in the description of the video. So I extracted those assets from a let's say open source Figma file, and also I will have the GitHub code for this project in the description, so you can just import the SVG files from my GitHub repository. Okay, so I imported the SVG files for the drawables for the pieces. So we have a black and white version for each piece. They are SVG files, so they are not going to work with Android. So if you try running on Android, you need to convert those SVG files to XML, to the Android vectors. So we can just like do something like this, new and vector asset, and import the SVG file from there. Like it will take some time, but yeah, then you can run the application on Android. So for me now, I'm only running on desktop, so it's okay. Okay, so now after importing the assets, we can go back to our pawn and go here. We'll have res.drawable.white, which is pawn white. I think we need to maybe let's have the build or something. Let's do something so we can have we can refresh the drawables. So here we go. We can put the pawn white here and the pawn black. Okay, so now we have the drawables depending on the color of the piece. So now let's go to the available moves. We have so we have the list of pieces here, and we have and you need to return the available moves. So let's start by creating a mutable set of int offset, which are the moves. And I think we can change this list to set. So set of int offset, because like we don't need to return the same position twice. Yeah, so yeah. Okay, now let's return those moves, and here we need to put the logic for the moves of pawn. So let's go back to our application and see what are the conditions that we need to deal with. So we have the pawn, like it goes upward in two, it has two movements if it is the first move. So if it is like the y is 2 or 7, and it has a single movement otherwise. And also if there is an enemy in the diagonal in upward, left or right, so it can capture those enemies. So it only eats enemies from the diagonal. So we have those three conditions that we need to handle. Okay, so we will start building this with let's say the ugly fastest way, and then we will start improving it and like making it the Kotlin way and make it much better. Also, like we have a lot of duplicated logic between pieces, so we need to have somehow have like a way to share this logic. For example, like we have the queen, it can go in the diagonal, which is the same movement for the bishop. Also the rook is like can move on all straight directions, which is the same for the queen as well. Also the pawn goes straight but with some limitations and only capture in the diagonal, so there is some like is it the same actually. Also the king is it the same as the queen. He can move into all directions but with a maximum of one movement. So we have some common things between different pieces. So when we start building the logic for the movements for each piece, we will see that we have a lot of duplicated code. So we will start by doing it the ugly way, as I said, and then we'll start improving it. So for the pawn, like going forward is different. If the pawn is black, he's going to go down, and if the pawn is white, he's going to go up. So we need to check this, which is the direction. So we have val direction equal if color dot is white, we will put 1, else -1. So which is this is the direction of the pawn, if he's going to go upward or downward. Okay, now we need to check if this is the first move. So is first move equal so this one, if he is white and the y is 2, no, so this is the first move. And also if the pawn is black and the y is 7, it is the first move as well. So we will have something like this: position dot y equal to, and color is white, or sorry, position dot y equals 7 and color is black. So this way we can check if the pawn is if this is the first move for the pawn, and also this way we can know if we are going to go maximum of 2 movement or 1 movement. Okay, so let's start by going forward. So we have the position of the pawn. We need to check the next position. So next, let's say that, okay, let's next position, and it's going to be something like int offset the same x, which is position dot x, and for the y we will have position dot y plus direction. So if the direction is 1, we'll have +1. If his y +1, otherwise -1, which is black. So this is the case. So going forward for white is from 5 to 6 +1, and for black it's the opposite. So going forward is having minus in the y, so from 7 to 6 or to 5. Okay, so this is the next position. Let's say let's put like next position 1 or something, and let's add this to the moves. But before adding this to the moves, this one is only valid when there is no piece in front of it. So if we have, for example, in this case, if we have another piece here, we can't move to this position. So we need to check that there is no piece there. So we will have maybe next piece 1, and which is pieces dot filter, and you can filter or find sorry, it dot position equal next position 1. So if next piece 1 is not or is null, we will add this move to moves. So now what we are doing is if there is no piece in front of this pawn, we will add the spot like in front of it to the possible moves, and we are going to repeat this one for the next movement. So for the second, for this one, like we will get the next position 2, and we will have direction multiplied by 2, and we'll repeat this. So as you can see, like it's it's something repeated here, and if we have Rook or something else like other than the pound, we will be repeating this for all the spots, like for maybe here in this case for 4 or 5 or 6 or whatever. So we know that here we need to use a loop, and we need to loop through the positions and check for each position. So there is a pattern that is repeated here. So let's go and start creating something more generic and valid for more cases, because in this case it's not like if you're going to do this, it will work, but as I said before, it's the ugly way. And yeah, next piece 2 and next position 2. So here we need to check if the next piece 2 equal null and is first move. So this one is going to check the second position, which is this one for the pound. It needs to be empty, and also it needs to be the first move of the pound, and also like the first position needs to be empty, because you can't jump like you can jump if you can't move to the first position, you can't move to the second one. So here, when we are going to build the loop, as soon as we meet an enemy, we are going to break the loop and not keep searching for other places. Okay, so now I think we have a better idea on how our loop is going to look like, because like we can actually see the pattern repeated here. We can have the y changing, so we can see that we are incrementing the y position, and then we go and find the target piece from the pieces and check if it is empty, and we add it as a possible move. So like, this is the pattern repeated. So let's get started. Okay, so let's start by creating a new file. I'm going to call it piece movement helper. So we will go in a functional way now. We will move from OP, and like for this like we will need some helper functions, and this is the good thing about Kotlin, like we can switch from functional to OP depending on the case. So here we will have some core helper functions available, which we can use for our movements. Okay, so in this piece movement helper class file, we are going to start by creating an extension function piece get moves. So this is an extension function for the piece, and it's going to return a set of int offset, which are the possible movements for this piece. So this will be our core function. It's going to be a generic one, like it will work for all the cases. So what the logic that we are going to have here is that we have a piece, and it's going to go somewhere in the map. It depends on the movement of this piece, and then we will see if it encounters an enemy, it can capture it, and we will stop, and so on. So we need to have the state of other pieces, so we need to pass the list of pieces, so we can know if we are in front of an enemy or an ally or whatever. And also we're going to pass the max movements, so which is going to be an integer, and we can give it the default value of 7. So this one is so here we are going to loop through all the possible movements for this piece, and like it's going to be from 1 to 7. For example, let's take the example of the queen here, for example. So this is the move number 1, move number 2, number 3, number 4, number 5, and so on. So the maximum is 7 for all pieces, and if in case we need to set a maximum for example for the king of 1, we can set max movement 1. So we will need this for the king and the pawn. So this get moves is going to be available for one direction, so we're going to repeat it for every direction. So here we're going to for each direction. So the idea is that we are going to loop through each direction. So for example, we will loop from the position of the piece, and will go upward or downward or in the diagonal. It depends on the case. So let's see how this is going to work. So first we'll start by creating a mutable set of moves, which is going to be an int offset, and let's return it. Okay, so now we are going to make a for loop. So we'll have I in 1 to max movements. So this is going to be the index or the number of movements. So this is not movement number 1, number 2, and until we reach the max movements. And then like we will give the color of this function the ability to set the offset depending on the movement. So let's see how we are going to deal with this. We'll have val offset, which is the target offset. Let's call it target offset, and we will create a lambda here called get position or get offset or whatever, and we will pass an int to it, and it's going to return an int offset. So let's call it here target position, it's better, and we will call get position. So how this is going to be useful, so for example, if we have a movement upward, the number 1 of the movement is going to add +1 to the y, and it's not going to touch the x, for example. And movement number 2 is going to add 2 to the y. And let's say that we are going in the diagonal, we are adding 1 to x and 1 to y, and so on. And let's say we have like maybe we are the black team. So having a movement downward is going to -1 in y axis. So using this get position lambda, we make this get moves more generic, and like when we call this the get moves function, we can decide what position we need to go. So here we can add a check if so we can get the target piece. So we can have pieces dot find it dot position equal target position. So here for this target piece, we will see if the next possible move, if there is a piece there or not. So if the target piece is not null, so there is something, we are going to break. So when there is a piece, we are not going to continue the movement. So for example here, for let's move this one. So here for the queen, there is a piece here, we will stop there. And here for example there is a piece as well, but it's not an enemy, and we stop there. So that's why we need to add the break when there is a target piece. Also, we need to check if the target piece color is not equal the current piece color. If it's not, then we can add it to the possible moves. So we'll add the target position as a possible move. So if we reach a piece, for example here we have a piece in this movement and it's an enemy, so it's a possible move. We are going to break, but we will add this position as a possible move. But if it's not an enemy, for example this one or this one or this one, we are not going to add it as a possible move. So that's how it's going to work. Okay. So now otherwise, if there is no enemy piece, like if there is nothing, we will just we will add the position as a possible move. Okay, so that's it for this function. We have all the rules that we need. So like it's really simple actually, but that's the rules of the chess, or at least like the general movement rules. So here if we are looping through the movements, and if we encounter an enemy piece, we will add it as a possible move, and that's it, we will break. Otherwise, if we will have empty positions, we will keep adding those positions as a possible moves. Okay, good. So now what we are going to do is we will create an enum class. Let's call it straight movement, and we'll have up, down, and left and right. So we will have those different straight movements. And why we have this one, so now we can create a function called get straight movement, or get straight moves, and then it's going to accept the same parameters as this one, but now we will add another parameter, which is the movement. So if it is upward, downward, left or right. Okay, so this is going to return the same set of int offset. And now we are going to use this get position, and now like the magic is going to happen. So we'll have return get moves, and we'll pass like the same parameters. Let's keep this one for now. Let's keep it empty, just pass the other parameters. So max movements and max movements. Okay, so now we'll have a when block, so when movement, and let's add remaining branches. Oh, sorry, delegates. Okay, so now if we are going to move upward, and here we have the index of the movement. So what we are going to do is add 1 multiplied by the index of movement to the y-axis. So we will have int I will have like the current position dot copy y equal or let's create it from 0, it's better. So we'll have int offset x equal position dot x, which is the position is coming from the piece, is the current x position. We will keep it the same, and for the y position we'll have the y position plus it, which is the index of the movement, which is going to be from 1 to max movements. So we'll have plus here. So let's copy the same block to the down, but for down movement we'll have minus, because when we are moving down, we have this -1. So let's make it clear here that we are going to use the same coordinates as the chessboard, which are like this position is going to be 8a, which is like for the characters we are going to use the char code for each character, but yeah, like for the y we have it like this. So it's not going to be like 1 2 3, no, it's going to be the opposite. That's why when we move down we have -1. So we still don't like go to this part of coordinates, but that's how it's going to work. So that's why we have this -1. So if let's say if you have the coordinates, the y coordinates going from 1 to 8, we'll have the opposite, like we'll have minus here and plus. It depends on the coordinate system that you have, but we are building a chess game, so we are following the coordinates of the chessboard. Okay, so for the left it's the same. So we will keep the position y the same, and we will change the position x, which is going to be -8. So when we move left, for example, this is a left movement, so we'll have -1 here. So as I said, okay, here the characters are sorted, so you can think of this as 1 2 3 4 5, whatever. It's just -1 and +1. So for the right movement we'll do the same thing, but instead of -8 we'll have plus. And yeah, so that's how we are going to get our straight moves. I don't need this one, sorry. So I hope this is clear. So here, like this lambda is going to work for here when we loop through movements, and we will get the correct position for each move. So we will pass the index of the movement and we will get the position. It depends. So if it depends on the direction of the movement. Okay, so let's try to use this one in the bound. So let's delete everything here, and let's just let's delete this one, and let's have get straight moves. Let's pass pieces equal pieces, and movement equal if color is white. So if white, we are moving up, and if the color is black, we are moving down. So straight movement up, else straight movement down. And we will have max movements. So for the max movements, val is like, we need to have the is first move that we've done before, which is the same position.y equal 2, and color is white, and we'll have our position y equals 7 and color is black. So here, if is first move, we'll have max movements 2, otherwise we have 1. So as you can see, it's much more simpler this way, and like we can use this for all other pieces. Of course, it's still missing a few things, but yeah, we are still improving this one. Okay, so now we need to test our work. So we don't have the UI yet, so let's try some testing. So let's have some test code, and I'll add the Kotlin test dependency. So let's create a common test package, and inside common test I will create a pieces package, and we are going to test the pound class. So let's create a new class pound test, and let's test the different cases for the pound. So we have 3 different cases. So if is first move, we can move we can have 2 movements forward. Okay, and here we have if is not first move, we can have 1 movement forward, and we can capture enemies in diagonal forward. So like we can't go backward to capture enemies, so in diagonal, but it's forward as well. So we have those 3 cases that we need to test. So before this, I'm going to create a new package here called board, and I will create a new file. I'll call it constants. So here what I'm going to do is we need to have the x coordinates and the y coordinates of our board. So as we said before, we will follow the chess rules. So what we are going to have is I'll create a val called board x coordinates, which is a list of support, which is a list of 8. And what I'm going to do is we'll have the char a code plus 8. So this is going to generate the char code for all of those characters from A to H, which is the coordinates of the chessboard. So this one is going to be from A to H, and you will have board y coordinates, which needs to be from 8 to 1, and this is going to be 8 minus 8. So we'll have 8 minus 1 until 8 minus 0 until 8 minus 7, which is going to be from 8 to 7. So this is we can have a range or a list for this, doesn't matter. And we are going to need this in our UI later for looping and building this grid using rows and columns, and for having a specific coordinate for each spot and try to get the correct piece for each position. Okay, so why I created this one this now is because we need to use it we can use it on testing as well, and we can make things easier and avoid having statics. Okay, so let's get started. Before this, I'm going to create 2 demo pieces. So demo white piece equal, I'll create a bound of color white, and position, let's say int offset, like I'll put any position, but then we will change it. So board x coordinates first and y equal board y coordinates first, and we will have a demo black piece. Okay, good. So then let's start our test cases. So we'll start by test move forward. So now we are going to test if we can move just one movement forward. So we will create our bound, which is going to be of color white, let's say, and position so int offset. We can choose the first x coordinate, and okay, we can choose the y number 2. So we can have this bound, so y2 and a, which is the board x coordinate first, or we can just have a if we want. Okay, so we have now our bound, which is a2, and we are going to try to move forward. So so let's try to get the moves equal bound get moves. Let's pass get available moves, and let's pass the pieces, which is the list of piece. We only have this bound for now, and we need to assert that moves dot size equal 1. Assert equals move the size equal 1, and also we need to assert that assert equals moves first move needs to be int offset. So we need to have an x a and y equal 3. So the possible move needs to be this one. Okay. So for this we will have assert true, and we need to check that the moves are greater than 1, or sorry, greater than 2. than 0. All the moves is not empty actually. Okay, why this? Because now like this one is like it's the first move of this pawn, and it can move to like 2 movements, and we are only testing the first move. So test first move forward, and we can run this on desktop and check if everything is working fine. Okay, so our test is passing, and we have a correct move for this piece. Okay, so now let's try to test second move forward. I'll copy this code. So I'll have test second move forward true, let's say. So we have the second move forward. I'm just choosing those names now, so they're not like the best to describe the situation here, but here this test function is going to be for testing the second move if it's true, so we can move to the second position. So now we need to check that we'll have assert equals, and we need to check that the moves are 2, so we need to have 2 moves, and also we need to check that the first one is this, and the second one needs to be so yes. Okay, so let's change it to a list, and so we can get the element. I'm worried like maybe this the set is going to sort the moves somehow, so let's just have assert true and just assert that the moves contain this one. So assert true moves, let's assert that this one is in moves, and also let's assert the same thing for the second position, which is y equal 4. So here if we move this pawn, we need to get those 2 positions, a3 and a4. So those are the possible moves. So and the size needs to be 2. So that's how we can check that everything is working fine here. Let's run our test on desktop again, and everything is working good. So let's copy and paste this one again. Let's test that the false case. So let's put the pawn in position 3. So this means that this is not the first move of the pawn, so it's the second or anything else. So now we need to only get this position. We can't move 2 positions, so we need to set the size to 1, and we need to have so we need to have assert equals moves first, and it needs to be this one. So moves first needs to be number 4, which is the next position. So we need to we have only a single move, and it should be in this position. So let's run this test and check. Okay, it's working fine, and we don't have the second. Okay, so now what we need to test is if we have an enemy in front of us, we can't move forward. So so now we have test no possible moves. So let's create this pawn again, and now we will have an enemy which is going to be, so let's have the pieces, which is going to be a list of pawn, and we'll have white piece, and let's move the the demo black piece needs to be an enemy, and yeah, it can be an ally as well, but it's the same. So let's change the position, and let's choose like it needs to be in front of this pawn. So the position is going to be a and 4, xa, y4, and yeah, let's now get the moves, and we need to assert true that moves is empty, so there is no possible moves. Let's pass the pieces to the get available moves, and let's check. Okay, so here our test is failing. Why we have this? Okay, so okay, what we have here is like it's returning, it's adding the position of the enemy to the possible positions, and because yeah, that's what you have actually in our code. So we said that if the target piece is an enemy, we add it to the target positions, and that's correct for almost all pieces. Yeah, like it's the case, but only for pawn it's not the case. So we need to have a special condition here. We need to add a new thing for our get moves function, so it can work in a more generic way. So let's add a new parameter for the pawn, can capture boolean equal true. So by default this piece can capture enemies, but if we have can capture false, we need to we need to not be able to capture enemies. So let's add it here. So now what we have if we want to add the enemy position as a possible movement, like he needs to be an enemy, and also you need to have the can capture true. Okay, so let's pass it here as well. So let's have the can capture equal true. Okay, so let's remove the default values from this one. Okay, so now let's go to the pawn, and let's have the can capture equal false, and let's go back to our test and run it and see. Okay, now our test is passing successfully, and we can capture and we can capture this, and we can't ignore this enemy. Okay, this is good. We can also add another test case in case if we have an ally in front of us, but it's not that important for now. But yeah, it's important, but it's going to be a lot of repetitive things. So yeah, you can add it if you want. So let's go back to our get moves function. Now after we have those constants, those board x and y coordinates, we need to check that our piece is inside the board, because we can move, we can pass a position that is outside the board. So if for some reason we passed the board, we need to break the loop. So if target position dot x is not in board x coordinates, or target position dot y is not in board y coordinates, we need to break this loop. And yeah, so in this case, we can, this case is going to be entered, let's say if we have for example this queen, so it's going down here, so, and the loop is going to keep is going to continue working until it reaches the max movement, which is the 7. So we'll check on this one, which is 0 and -1 and so on. And yeah, so we need to check that 0 it's not in the y coordinates of the chessboard, so we need to break. That's why we need to add this check. Okay, good. So now we have those test functions for our pawn. We are testing the forward movement, and I think this test is enough for the forward movement, and it's working fine. Now what we need to test is diagonal movement, or diagonal moves. let's add this here. So forward moves. Okay, so for the pound it has this special case. So test capture enemy. Let's get our pound again, and let's get this enemy. Let's get all of this code. I think like we have some repetitive code here. We can have some utils to make tests easier and to simplify this, but yeah, feel free to optimize this code more. Okay, so we will have an enemy which is in B4. So this is our piece here in A3, and we'll have the enemy here. Let's try to simulate this one. Okay, this is our enemy. It's in B4. So we need to be able to capture this enemy, and this one needs to be a possible movement for us. So the moves, we don't care about the size of the moves, but what we care about is assert equals or assert true. Okay, we have assert contain here. Maybe you can use it. So assert contain moves, it needs to be like, need to have this demo black piece position. So it needs to be one of the possible movements. And of course, this is going to fail right now because we don't have the logic for the diagonal movements for the pound yet. We only have, so if we go to the pound class, we only have this get straight moves. So we only implemented the straight movements, not the diagonal movements. Okay, I think maybe we can move this to a separate file for better separation. So let's have this on here, and let's create a new file. Let's call it diagonal movement, and we'll have a new enum class diagonal movement. So for this diagonal movement, we'll have also 4 values, which is up left and upright and down left and down right. Okay, good. So now let's we will have like a similar function, a function similar to this one, and we will have get diagonal movements or get diagonal moves. And yeah, this one needs to be diagonal moves. Let's change those. So up left, up right, and down left and down right. So everything is the same, just this get position. As we said before, all the magic is happening here in this lambda. So now we need to change how we are going to deal with movements in this get position function. So we can even skip, like we can have some custom rules, like maybe this one skips the white positions or something, like it only goes in black positions. We can have any rule we want. So but for now we will keep the usual rules. So for the diagonal movements, we are going to have the up left. We are going to change the x and y. I'm going to change both of them. So we'll have position x minus it, because for the left we have the minus and for up we have the plus. The upright is, so we have plus for the y for the up and plus 8 for the right as well. For down left, yeah, we have minus, and down right we have minus as well. So for this one, for example, for the up left, which is this one, this one up left, and we are going up. So this is movement number 1. What we are going to do is we have -1 in x and +1 in y. So this is up. And for the upright, we have +1 in x and +1 in y. And this is down right and down left. We have 2 of them here. So yeah, so here we are changing the x and y positions, both of them at the same time. That's how the get diagonal moves work. So we can use this one in the pound. Let's have like plus here or something. We will improve it later, but yeah, let's just have this one for now to check that everything is working. So we have diagonal moves, and we'll have upright, we have down right, yeah, and we don't need this max movement. We have like a max movement of only one in diagonal movement for the pound, and it can capture, so we'll remove this condition. I will add another one because we go like in two directions in diagonal, like go up right and up left, or down right and down left. Okay, so that's what we have. We will improve this one. We are going to build a DSL, which is the Kotlin way for doing those builders. Yeah, but for now we need to just get our test passing, and then we will move on improving this one with building a DSL, and we will have a nice builder, better than this. Okay, so now if we try to run our function, let's see what we have. Okay, it's working fine successfully, and yeah, the black piece now is part of our moves, and we can capture it. But now if we try to run the other test of the pound, it's going to fail. So let's try to run all the tests, and yeah, we have like 3 failing tests. So what's happening now is each time we have an available diagonal move, and we just move. So it doesn't matter if we only capture or it's just an empty space. The pawn is going to move in any empty diagonal position. So what we need to add is we need a condition to say only go in this movement if you can capture a piece. Like don't go if there is no enemy there. So that's how the pawn works when he's in the diagonal. So we will add another flag here, another boolean, so which is capture only, and it will be false by default, and only the pawn in the diagonal have this one as true. So when this one is true, we are not going to go to empty places. So this is like here we go to an empty place, which is like the target piece is null here, and we go to this one. So when we have it set to true, this is not going to be possible. So we will have else if capture only. So in this case, what we are going to do is we will break the loop. So if capture only and there is no enemy in this position, we will just break, and we are not going to add this position in the available moves. We can add it here as well, like if target piece is not null or capture only, but yeah, let's keep it cleaner this way. So now if we try to run the pound tests again, it should be running successfully. Oh sorry, we need to pass it as well, of course here. So capture only, and let's add it here. Let's have a default value of false, because most of the pieces are not going to be like capture only. It's only something that we need for the pound, and we need to go to the pound, and we have like here we have capture only set to true, and capture only set to true for the diagonal moves. And now if we try to run the tests again, it should be running successfully. Good, we have all our tests running successfully, which is good. Okay, nice. So now we have those functionalities that makes the pound works correctly, and yeah, but this one, like I don't like this too much, this plus and all of those things. So let's do this the Kotlin way, and let's use the power of Kotlin to make this like a fancier and better code. So I'll create a new directory here, package called DSL, and also I'll move all of those files inside the DSL, and and I'll create a new class. I'll call it piece movement builder. Okay, so now inside this class we're going to take the piece as a parameter, and also we're going to take the pieces. So, and why we are doing this, so if we need to have like chain calls like this one here, we don't need to to pass the pieces each time. Yeah, that's why. Okay, so at least we can avoid this. Okay, so let's go back to our builder. We will have private val moves equal mutable state of mutable set of int offset. So here we are using the builder design pattern, but yeah, we are not going to use it like we will add something to it, which is we'll add a DSL to make it better, and to make it better to use. Yeah, so yeah, we'll have this build function which is going to return the possible moves, and I'll add another function which is straight moves. So in the builder design pattern, you need to return the builder with each method. Only for the build you return the result, but here we are going to use this builder for the DSL, so we don't need to return anything. And yeah, here we'll have moves dot add all. We'll add all from piece dot get straight moves. So we need to get those parameters and pass them from here. So yeah, like this. We will have those parameters, and we will have pieces, have everything. So pieces and movement, max movement, and can capture only. Okay, so we have this straight moves method that we are going to use and yeah, then we can just create another one for the diagonal moves. So get diagonal moves, let's call it diagonal move, and yeah, we need to change this to diagonal movement. Okay, good. So now our builder is ready. So we can just, like, if you add this as a return type, if you add the builder as a return type and return it each time, you have the builder design pattern, but we don't need it in this case. As I said, we will have a DSL, so we'll have this build piece movement, and for this one I'm going to pass a piece and pieces. We'll pass it once, and so to avoid keep passing it to each method of the builder. And we will have the block piece movement builder. This is going to be our lambda function, and then yeah, we are going to create our builder. So piece equal piece and pieces equal pieces, and then we'll have the builder. We'll call the block, and we will return the builder dot build. Builder dot build, and we'll change the return type to set of int offset. So now we have this build piece movement that we can this function that we can use in our pound instead of this mess. So let's see how we can make things better here. So we don't need to pass the piece here. We can just have it as an extension function this way. So yeah, this, and we can have this here. Yeah, so this way at least we can reduce the number of parameters. We can pass pieces here, and we can have our DSL. So now we have straight moves. Let's pass those parameters, and we have diagonal moves. Let's pass those parameters as well, and let's copy and paste this again. We have this one. Okay, so let's remove this, and as you can see, this is more like it's much more better, and we can make it even better with changing those up and down with maybe forward and downward or something like that, and make it and change it depending on the color. So we have the piece and we have the color of the piece, but yeah, this is a possible improvement that we can do. But for now, that's good. We only need this in the pound anyway, so for other pieces it's going to be much easier and straightforward. So let's run our tests again to make sure that everything is working fine. So yeah, good. So our pound is working fine, and yeah, our functions are doing the job. So now let's move to the next pieces. So let's see what we have. So let's start with the Rook. So now we have everything that we need to build the other pieces. So it's going to be much easier now. So we have the Rook, which is going to implement the piece interface. We'll have the color and the position. Sorry. Yeah, and then we'll have the drawable, same as before. If the color is equal, if the color is white, we'll have resources dot drawable dot rook white. Else we'll have resources dot drawable rook black. Okay, now get available moves. It's going to be much simpler. We will have equal build piece movement plus pieces. You can change it to get piece movement. Also, like, can have better name. It's not a build actually. It's get piece moves, something like that. Yeah, we can choose the name that represents this the most. Okay, so now we have this. Only this one straight moves method, which is you need to pass a possible one of the straight movement. But for the Rook, we have all of the possible ones. So we don't. I think we don't need to repeat this one 4 times, but instead we can have a new one that doesn't take the movement as a parameter, but instead we can loop through all of the movements and do it this way. Yeah, this is going to be much better, and we can maybe you can call this one to make it better. So yeah. Okay, good. I think we can repeat the same thing for the diagonal moves. So we are going to loop through all of the diagonal movement enum class entries, and for each one we'll call the diagonal moves method. So this is going to make things much easier when because of most of the pieces move in all directions, in all straight moves, like all diagonal moves. So yeah, it doesn't make sense to keep repeating this method for each move. So let's go back to the Rook, and yeah, so instead of having keep passing the movement, straight movement down, left, and right and up, we can just have a single call for all the moves. So we have straight moves this way, and that's it. So this is everything that we need to set for the Rook to work. And yeah, so let's build the bishop. So I'll copy the Rook class and rename it to the bishop. So you have bishop white, bishop black, and here the same, so we'll have diagonal moves instead of straight moves, and that's it. Okay, good. Yeah, so now let's copy and paste this one as well, and let's have the queen, and yeah, queen white and queen black. So for the queen we'll have both, so we'll have straight moves and diagonal moves, and as you can see how much easier it is to composite those different movements, and you have a lot of flexibility here. Then we need to add the king, so we'll have the drawable for the king black, king white, and for the king we have all of the possible movements, but we have max movements of 1. So we have max movements of 1, straight and diagonal, both of them. Yeah, good. So that's it for the king. So yeah, so now we have all the pieces. The only missing one is the knight, which is a bit special, so it's not going to be the same as other pieces. Yeah, so we'll have the knight white and the knight the knight white image and the knight black image. And yeah, for the knight we need to have a new method here. So let's go back to this movement helper file where we have this get moves. So let's create a new function here. Let's call it get L moves, and yeah, let's pass the pieces and the position. Okay, so actually we don't need the position, we have the piece. So okay, so now we are going to create the same moves, mutable set of int offset and return moves, and then we will have all the different possible moves for the knight. So for the knight we have we can go to the can go to this up. So as you can see, if we choose this knight, for example, so we have like it's we can now where is it going to go. So it's going to go like two positions to the top and one to the left, or one to the right, or one to the top and 2 positions to the left and 2 positions to the right. So yeah, so we have like I think 8 possible positions for the knight, which are all of the possible positions that we can add to the current knight position, so we can get the possible positions for the knight. I know it's a bit confusing, but yeah, it's a lot easier for the knight. I'm just going to copy all of those positions, so we can go through them one by one. So we have this int offset -1, -2, so we can, which is going to be like this one, for example, -1 and -2, which is this is the position. We have also +1, -2, and so on. We have -2, -1, and yeah, we have here -2, -1, or +2, -1, and so on. We have like multiple 2 and 1s, and with different minus and like, so these are all of the possible positions that you can add to the current knight position, so we can get the correct moves. So yeah, so let's loop through this list, and I'm going to add the new, or let's call it target position, equal the current position plus the offset that we need to add. So let's add here the same check. Let's check that this position in the board, for example, like for this one, if you go 2 positions to the right and 1 down, it's not inside the board, so we need to add those checks. But here we are not going to break, but we are going to continue, because yeah, it's different here. Like even if this one is not in the board, or maybe this one is not in the board but this one is. So we'll keep checking on all the possible positions if they are on the board or not. Okay, so now let's have the target piece, which is pieces first, or find it dot position equal target position. And here it's much simpler. So if the target piece equal null, or the target piece dot color is not equal this dot color, we will add this move. So so here what we have, let's add the return type, avoid the error. So here what we have is, if the target position is empty or it's an enemy, this is a possible move. So that we don't need to have some custom rules for the knight. So that's enough for getting the L moves. So it's like a static way for doing this. Like maybe we can have a function to generate all of those offsets, but we don't have to. It's just static, so we can just put it like that. And yeah, so for the knight we can change this with get. So we need to add it here before. So we'll have in our builder, we need to add the get L moves, and we'll have moves dot add all piece dot get L moves, and we need to pass the pieces. So that's it. And then we can go back to the knight and use the get L moves, and this should be working fine. Okay, great. So now we have all the logic that we need for the pieces. So we have our pieces, and we have the get available moves methods implemented for each piece, and we have our nice DSL for like composing different rules of movements and return the possible moves for each piece. So this can be like customized, and it is scalable even if you're working with a different type of game, not just chess game, but we have a board and we have custom rules. We can use this approach of DSL. We can add a new piece, for example, which is like maybe stronger than the queen, that can go straight and diagonal, and can also have L moves and can jump through other pieces. Can have this as well. So it's you can see how easy it is to add this new rule to an existing piece. Okay, so you can also of course test all other pieces, but we don't have to. I mean, we don't need to waste time to paste those pieces, but of course if you're working on a real game, you need to add the test cases for all of those pieces. We do it for the pawn, and yeah, we can do it the same way for other different pieces. Okay, so now for the board, inside the board directory, I'm going to create a new class. I'll call it board. So in this class we'll have the logic for our application, and yeah, here we will have the state of the board, and it's going to be used inside our application to have the state of the game. So let's start by creating a list of pieces, which is going to be mutable state list of piece. I'm going to use the mutable state list of from compose, and yeah, we'll have another public copy of it, pieces.toList. Okay, good. So also we need to have the selected piece. So mutable state of, okay, I had those compose things. Mutable state of piece, which is going to be nullable. And yeah, so this is when we are going to set this one is when we click on a piece here, it's going to be the selected piece, and we will go to find the available moves for this selected piece. Okay, good. Let's put it as a private set. Also, we need to have the selected piece moves. So it's going to be mutable state of empty list. Let's have an empty list of int offset, so, or maybe empty set, it's better, empty set. Yeah, that's good. So here we will have the list of the possible moves, so which are those ones. So when we select a piece, we will put the possible moves into this state, so we can use it in compose and show the UI for those dots. And yeah, we can have also a player term, which is mutable state of piece.color.white. So I can start by the white player. And yeah, I think this is enough for now. So let's build the events that the user can do. So we have like actually two main events, which are selecting a piece and moving a piece by selecting a possible movement place. Okay, so let's build the first event, which is the select. I'll have the select piece method that accepts a piece as a parameter. So what we will have here, if the piece is the selected piece, or the piece.color. Okay, let's add this to the top. So if the piece.color is not player term, we will return. So you need to be the current player, so you can select the piece. And if the piece is the selected piece, we are going to clear the selection, otherwise we will select this piece. So let's have a private function for clearing selection. Let's call it here, and we'll have the selected piece equal null and the selected piece moves equal empty set. And then if otherwise, we will have the selected piece equal the current piece, and the selected piece moves is going to be equal piece.get available moves, and we will pass the pieces to the get available moves method. Okay, good. So now what we need to add is the event for moving the selected piece. So let's add it. So let's go and add add it to the top, and let's make this clear here. User events and private methods. Okay, so move selected piece, and we will pass the correspondent coordinates, the x and y, and here we are going to move the selected piece. So we are going to check if the selected piece is not null. So let's add the let, and okay, so now we need to have two checks. We need to check that this is a possible move, and also that the piece color is not the piece color, yeah, is not is the same as the player term. So let's have the first check that this is the first this is an available move. So let's go here and create this function is available. It's available move, and let's pass the x and y coordinates, and we are going to return a boolean. So this is very simple. We are just going to go to the selected piece moves, and we'll have any a.x equal x and a.y equal y. Okay, so this way we can check that at least we have an available move, and we can move to this position. Now in the selected piece here, we are going to check if it's not an available move. We are going to return. Also, if the piece if the piece dot color is not equal player turn, we are going to return. So we need to check that this is the correct player who is playing. Okay, good. So now we are going to move the piece if everything is good. So let's create a new private function here. Let's call it move piece. I need to pass, let's pass the piece and pass the offset where we need to move. So here we need to go and find the target piece, equal pieces, find e.position equal let's call it position. Okay, so now if the target piece is not null, we are going to remove it. So let's add a new method here for removing piece. So we are going to remove this one if it is not null. Otherwise, not otherwise, but also we are going to change the position of the piece that we want to move. So we have the position as a var, so we can change it directly, and if there is another piece on that position, we are going to remove it. So here in this remove piece, we are just going to go to the pieces and we will remove this one. Okay, good. So now we can go back to this move selected piece method, and now we can move our piece to the correct position. So let's move the piece, and the position is going to be int offset of x and y. And after that we need to clear the selection, because yeah, after moving the piece the selection is cleared. Yeah, and then we should switch the player turn. So let's create a new method. Let's call it switch player turn, and let's add it here. Private fun switch player turn equal. So if player turn white, turn equal black, else player turn equal white. Can move it outside the if statement, and we can have it this way. We can use the is white here, is white. Yeah, so this way we can switch the player turn after we have a successful move of the piece. So those are the two user events that we need to use. So yeah, so now I think we are ready to start building our UI, and let's see what we'll have. Let's close all of the tabs. Okay, so here let's create a new file called board UI, and inside this I'm going to create a new composable called board UI, which is going to take the board as a parameter, and also let's pass a modifier. Okay, so the board is going to be a grid, so we are going to have a column that has different rows. So let's create a column. So let's have a modifier. We'll add an aspect ratio of 1 and with fill max size. So to have a square board, and let's add a border of ADP, for example, and with white color. And let's add the padding of ADP. Okay, so now we need to look through all our coordinates and have a position or a board cell or whatever for each coordinate. So we already have the constants, the board x coordinates and the board y coordinates. We're going to use them. So for each y coordinate we'll have this y, and we will have a row. So for the row we are going to have a fill max width and weight of 100f. So we are going to divide the column height between the different rows, and we will have a board x coordinates. Maybe you can have this on top, and you can have for each. And here we need to get the piece. So now we need to get the piece by the x and y positions. So let's go to the board. We need to have a method for getting the piece. So let's have public methods which are not user events, and we have is available. Let's add get piece x and y. So this is going to return a piece, nullable piece, and its pieces dot find it.x equal x and it.y equal y. Oh, sorry, it.position.x and it.position.y. Okay, so so this method is going to return the piece, but here we are in compose. So if we can have something like this, board.get piece, and we pass the x and y, but there is no compose state here. Like the pieces are a compose state, like it's going to recompose when the pieces changes, when you add a new piece or when we remove a piece. But the problem is with position, when we move a piece, it's not going to listen to those changes. So the best way to handle this, we can change the positions of the piece to compose states, but we can change this position to a compose state, but it's not the best option. Like we are not going to have real control, or when we want the UI to be updated. So so for having like a better control, I think the best option is to add a new var here. Let's call it move increment or something, so which is going to be immutable state int state mutable int state of, have it is 0 private set. So this is we are going to increment this one each time we make a movement. So each time we want this get piece to be called again. So yeah, so now we are going to increment this when we move a piece. So we have this move selected piece, we will call the move increment plus here. and then we can add this as a key. We can have remember and add this as a key to make to execute this again. So let's go to the bottom. I think we can have here some helper function. We can have an extension function for board, and we can have remember piece at x and y, and it's going to be equal remember, and we'll have get piece at x and y. And here what we need to add is let's add the x and y as keys for the remember, and also we'll add the move increment. So each time the move increment is changes, so each time we change a piece, this code is going to be executed again, so we get the new correct piece for each position. So now let's use this one instead, remember piece at, which is going to be safer, and even in terms of performance it's going to be better. So we only make the calculation again when there is something changed. Okay, good. So what we need to add as well is we need to check that if this position is an available move. So we have is available move. So this is going to be used for showing the dots. So if it's an available move, we'll show this this dot here. Yeah, so for this let's have something like this. So we'll have a similar one to this remember. Don't need the move increment, but let's have a helper, an extension function here, board remember is available move. So let's pass an x and y, and it's going to return a boolean, and yeah, so remember, and we already have the is available move method inside the board. We are going to use it, but we need to add the keys. So let's add the x and y, and also we will add selected piece available moves, selected piece moves. So yeah, so we need to add this one, which is immutable state already. So when we select, when this one changes, this one is going to be called again. So which is going to give us correct results. So here we'll have the same thing, board dot remember available moves, and we'll have x and y. Okay, good. So I think this is all the data that we need. Now we can have here the board cell, which is the position inside the board. So I think it's better to create it as a separate component. So I'm going to create a new file. Let's call it board cell, and I'm going to have a composable function called board cell. It's going to take an x and y and piece, nullable piece, of course, because it can be an empty position. We will pass the board as well, and we will pass if it is an available move, and also of course the modifier. Never forget the modifier. Always add it for any composable. Okay. Okay, so so good. Now we have those are the parameters that we are going to need. So let's build the UI. So we need to have box, and let's fill the max size. I think we can set the size with from the parent. So let's call it from here. Let's add x equal x, y equal y, and piece, and let's pass everything is available move. And for the modifier, what I'm going to do is we'll have weight 1f and fill max height. So which is going to fill the max height of the row and divide the row width between those cells. So we will have squares this way, and it's going to be a responsive board that's going to work for all the devices. So as you can see here, our board is responsive, so that's why we are using the weight and not static sizes. Okay, so now inside this box, first of all, let's add those texts. So we have here the y values and here the x values, and why we have and when we have them is like when the y is 1, we have the x values, and when the x is a, we have the y values. So yeah, so let's add this. So when the x is a, which is the board x coordinates dot first, we will draw the y text. So text equal y dot toString, and let's have a font size of 14 sp, and this one is going to be alignment top start, and let's have a small padding, maybe 3 dp of padding, which is going to be good. Okay, good. And in the same way, we'll have if the y equal 1, we will draw the x text. So we'll have this one, and for the x text it's on the bottom end, as you can see. So this one in the bottom end, and this one in the top start. Okay, good. Now what we have is the piece. So if there is a piece, we need to show the image of the piece. So we already have it as a drawable resource. So we have image painter, and the same way you can have a URL or whatever, and you can use anything to represent the image. So here we decide to use drawables, and we'll have a painter resource, e.drawable, and content description, and we'll have a modifier. So this is here the image of the piece. Let's add a fill max size with a bit of padding, maybe 8 dp. Okay, so this is here we have the image of the piece, which is going to be clickable. We need to click the piece, and so when the user is going to click a piece, we are going to call the select piece method in the board. So let's add a clickable modifier here. I prefer to add interaction source. I prefer to disable the indication, so let's add mutable interaction source and indication null. And yeah, let's call the board.select piece method, which is, and pass it. Okay, good. And then also we need to check if this is an available move. We will add another box, which is the dot that we are going to draw. So which needs to be aligned to the center, alignment center, and fill max size. And let's have it draw behind, draw circle, which is going to be let's fix the color after this. So it's going to have the radius, for example, for size dot width divided by 4, or maybe by 6 should be good. And the center is the center of the component. Okay, good. So this way we can have images, can have pieces in place, and we can have the positions, which is good. Let's call the board UI in our app. So maybe you can have a box, fill max size. Let's call the board UI here. Let's make this immutable, and let's create a remember board function, which is going to return the board. So I'm doing this the compose way. So yeah, we have our board here, remember board, and we are passing it to the board UI. So let's try running our application on desktop. We should get an empty board actually, because we don't have pieces, but yeah, let's see. Okay, good. So we have the numbers here, which are correct, and yeah, things looks good. I think everything is good now. Okay, let's have the alignment set to center. And there is something that we forgot. So in the cell for the X, we are not going to show the X, the char code, but instead we are going to create it to move it to char. So we have X to char and then to string. Okay, so now we need some colors. So I'm going to create a new file. Call it colors. I imported those colors from the Figma assets linked into the description. Also, you can copy them from the GitHub repository. So we have an active color, dark color, and the light color. So in the cell, we can have different background colors and different text colors. So let's have while background color, it's going to be equal when the piece is not null. So you have a piece and the piece is selected, it's going to be the active color. So in this case we'll use the active color, which is this which is this case. When we select a piece, the background needs to be active. Okay, so and if the x plus y is divided by 2, we will have dark color. So otherwise we will have the light color. So this is how we can know if the position is dark or white in the chess. So we can, the x and 2 needs to be divided by the x and y needs to be divided by 2. But also of course this is for the case of using, for our case, for using the char codes with the positions from 1 to 8. Okay, so now let's create the text color the same way. I think that I'm going to copy this one, which is going to be easier. And we will have the light color and we will have dark color. And here in the case of active, let's use maybe white, just a white color. So let's add the background to the box. So background color, and let's add the text color here to the text. And yes, so also let's change the circle that we have in blue here with the active color. Good. Let's try to run the application again and see if you have a nice UI. Okay, good. We have this nice UI now. The board is good. So now we need to put the pieces in place. Okay, so let's try to put like some pieces and see if this is working. So let's go to the board, maybe in the init block we'll go to pieces, and let's have add, for example, let's create a pawn, color white, and let's have a position of maybe x equal a and y equal 2 maybe. And let's add another one which is black with an a equal with an x equal a as well, and 7 for y. Let's try to run this and see if it's going to work. Okay, here we go. So as you can see now we have those 2 pawns on the correct positions, a2 and a7, and yeah, we can move. So it's the white turn. We can move the black, so we can move we can have 2 movements, upward or single one, as you can see. Okay, now what we have, the selection is working fine, but moving the piece is not working. So we still don't have the event of when the user clicks the possible movement position, so which is this one. Okay, so let's add a clickable here as well without an indication, and let's have move selected piece to x and y, to this position. So I prefer adding names to methods. So piece. Okay, so here we should be moving the selected piece to the positions of the clicked cell. So let's see. Here we go. So now we moved the white piece, and we can select it again. You can select the black, you can move it, you can select the white, you can move it, and now we are stuck. Okay, so we are not going to keep adding all of those pieces, but instead there's something much easier that we can do, which is we can decode and encode those pieces into strings, and then we can just have a decoded board with all of in a single string, and then we can use it to build the board. So let's see how we can do this. And this way, with decoding and encoding the pieces, we can save the game and just and return the saved state, so which is the thing that we have here. So if you go here, try to remember the places. For example, the queen is in D3. Let's save the game here. I'll go back and I'll click load game. I'll choose game 1. So as you can see, the queen is in D3 and everything is in the same position. So we are going to do this the same thing. So we need to save the board state into a single string, and then we can decode it again into pieces. Okay, let's see how we are going to do this. So let's move to the piece interface, and we can either add the correspondent methods here, or we can have a separate encoder decoder, but for simplicity I will add them here. So we'll have an encode method inside the piece, which is going to return a string. So here we will just have color code equal color dot name dot first. I'll take the first character from the color, and we need the type for each piece. So I will add a new property here, type, which is a char. We need to keep it as minimal as we can. So for each piece, I'll go and create a const val type, which is for the bishop it's going to be B, for the king it's going to be K, for the knight it will be N because we have the K for the king, for the pawn it's going to be P, for the queen it's going to be Q, and for the rook it's going to be R. And then we will override the type and the type value here, and we'll pass the type for each piece. So here the queen has its own type, sorry. Yeah, so, and the pawn will have its type, same for the knight and the king and the bishop. So now each piece has a type, which is a letter specifically for this piece. And now we can encode the pieces, and we can have like a string from like 4 characters, which contains the type, the color code, and the X position and the Y position. So you can have a string builder, and we can append the type and append the color code to string, sorry, and also we can append the position X and append the position Y. So here we have a small issue, which is the position X is the code of those characters, which is like it's 2 characters here. So when we change it to string, we will have 50 something, which that we can store in a single character. So what we are going to do is we will have minus board X coordinates dot mine, the mean one, and here we'll have the same for the Y. We don't need it for the Y, but we'll have it to make things the same way. So what we are going to do is, when encoding we will have this minus, and when decoding we will have plus board X coordinate mine again. So we are going to normalize the X and Y coordinates and make them to a 0 based coordinates. So are making actually a transition for the board by those mean X and Y. Okay, so we need this only for the X to make it possible to store them into a single character. So we can have as minimal characters as we can. And let's have a const val here for encoded piece length, which is going to be constant, which is 4. Needs to be 4 always. Okay, so now let's have a factory method. So we're going to use the factory method or the factory function design pattern, and let's call it decode, which is going to receive the encoded piece string and return a piece. So here what we are going to have is we will have a type and a color and x and y from the encoded piece. We will change it to char array, so we can okay, so now let's create the piece color again. So the piece color is going to be equal color dot entries dot find it dot name equal color it dot name dot first. So so before, like when we save the color, we are saving the first character of the color, which is y and which is y and b. So now we are retrieving the colors the same way, otherwise we will throw an illegal argument exception. So invalid piece color. Okay, so now let's retrieve the position. So we'll have position equal int offset. So x we'll have x dot digit to int. Of course we need to use digit to int to so we get the digit from this int instead of having the x transformed to character or something else. And we will add board x coordinates dot mean and x equal and y equal y digit to int plus board y coordinates dot mean. So now we will make the opposite transition that we made before, or opposite translation actually. So here we have the minus, and then we have the plus, and we correct the positions. So now we can check on the type. So if the type is pound type constant, we will have a pound equal piece color position. And yeah, I can just copy this because it's just repeated code. Yeah, so we have, depending on the type of each piece, we are going to create the correct piece. Otherwise we'll throw an invalid piece type. We'll have illegal argument exception. Okay, so this is the decode factory function that we have. So we're going to use this one if we want to initialize the board. So let's go to the constants here. Maybe it's not the correct place, but anyway, so I will have decode pieces and encoded pieces, which is a string. It's going to return, let's say, a result of list of piece, or maybe not need to return a result, but I'll trust my my code anyway. But you can return a result to avoid errors, but because you can't make sure that these encoded pieces are passed correctly. So, but for making things simpler, I will just return a list of pieces, and we will have pieces equal mutable list of piece. And okay, so now we have this encoded pieces string, and each piece is 4 characters. So we are going to loop through this string and take 4 characters by 4 and try to decode it as a piece. So what we're going to do is index equals 0, and we will loop if this index is smaller than the length of the string. We'll keep looping. So here we'll have encoded piece, which is going to be equal encoded pieces dot substring, and we will substring it like from index to index plus piece dot encoded piece length. So we are dividing this string 4 by 4, and try to encode each four characters. So yeah, so we'll add the decoded piece to the list. So we'll have piece.decode, and let's pass the encoded piece to it, and index plus equal piece.encoded piece length. So we'll add the 4 here, plus equal 4 for each iteration, because we are taking 4 characters for on each iteration. And yeah, so here we will keep decoding the string. Like we can do something much easier with, like, maybe we can have a chunked for, which is going to return a list of strings of 4, and you can have a map or something, and piece.encode or decode. You can have something like this, but yeah, we are doing it the most yeah, this is the most performant way. So yeah, it's not the most elegant way, but performance, I think it is important in these cases. For this case, it's not that big difference, but anyway, you get the point. Just think of having very big strings. This should be the best option to do it. Okay, so now we have this decode pieces. I already created a string for the initial positions for the encoded pieces. So those are this is the string for the encoded positions of the pieces. So we can use it to initialize the board. So this is, you can copy this from the GitHub repository, or you can even add the pieces by yourself, like one by one with the add, and then try to decode them and get this string. That's how I did it. So here in the init block, we can have pieces, add all, get pieces, or decode pieces, and we can have the initial pieces position, or the initial encoded pieces position. And yeah, we can decode them and add them to the list of pieces. So this way, if we run the application again, yeah, we have everything in place. I think we have an error here. There is a king. This king should be white. So what is the position? He's in E2, which is 0, 1, 2, 3, 4. I think he's this one, or this one. Yeah, this one. Let's try to run again. Not sure why. I think that we have yeah, the error is here. I get it. Yeah, we have king black for it should be king white here. Okay, it's fixed now. So as you can see, we have all the pieces in place, and we can start playing. So yeah, everything is working fine, as you can see. So the pieces are moving on the correct positions. As you can see, the queen can move on all directions. Yeah, so the same for the knight. The rook is moving fine. The bishop is working fine. The king is moving of a maximum of a single position. So yeah, that's the chess game. Everything is working. So we still don't have the logic for the checkmate and for checking if you're dead or not. I'm going to add this logic into the GitHub repository, because I don't want to make the video much longer, and it's not the essential part and the main reason for why I did this. So if you want the other parts of the rules and preventing the player from moving when the king is in danger, so check the GitHub repo. You will get much more features there. And yeah, I hope this video was helpful. Thank you. See you next time. Hopefully you are going to take another game, maybe the Tetris game. It's a good example as well for having these concepts of object oriented. Also, an inventory is a really good way to learn new things here. So having different items in the inventory, each item has a price. You can buy items, you can apply items to the player or whatever, and have a different effects to the strength and the health and so on. So yeah, I'm not sure yet what is the video of the next part of this series, but yeah, hopefully we will have a series of videos. We will talk about all of those different concepts. We'll have real examples, the same as this one, this chess game example, where we are here, where we see the DSLs, the Kotlin DSLs, with the Kotlin way for doing the builder design pattern. It's the same to the builder design pattern actually, but with a more elegant way. Also, we see here in the piece the factory method or the factory function design pattern, where we are creating the piece from an encoded piece string. Also, yeah, we saw a lot of things here. Also, we have the inheritance and how we deal with the piece, and why we choose an interface for the piece, and passing the color here as an enum class inside the piece. Yeah, and how we have this this nice DSL for composing different conditions and different moves types. Yeah, so I hope this video was helpful and you learned new things. See you next time.